All right, so tell me, how did you describe the upper left scatter plot? Strong positive or fairly strong positive? I like that. I'm going to call this fairly strong positive. If you just said strong positive, I would accept that.
With these, do we have to use the ly word always too, or no?
It's a good idea. It's a good idea. Sometimes you wouldn't, like if it's, well, with most of these I would use an ly word. Some of them, like if it looks like almost a perfectly straight line, I think you'd be okay with saying like that's strong. So, the one in the middle on the top, how did we describe that one? Moderate negative. The last one on the top, strong positive. I would even maybe go with very strong positive, but definitely strong positive. Or sorry, negative, negative. You guys are right. I was looking at the other one. Sorry. Strong negative. All right. Why are we saying negative, just to clarify? Because it's going down. It has a negative slope to it, yes. All right. Lower left. Moderate positive. Is that what you guys put?
I put weak.
I would say weak positive on this one. Weak positive. All right, in the middle. Weak positive. I'm even going to go with very weak positive. All right, and the last one. Moderate negative. Yes. Maybe. I think that one's more of a moderate than a weak. Like if you compare it to the one in the middle on the bottom, I think it's stronger than that one.
If you put like a line through it, you can be multiple on that one. If you put it through that one, you can't.
Yeah, like here's what it looks like if I draw a line through it. It's the dots are reasonably close to the line. Like some of them are a little bit cloudy, but all together I think they're like clinging around-ish the line. All right, so we are going to learn about a new variable. I don't know why I changed that to orange. Let me fix that. So down in the corner of each of these graphs, there's something called an R value. The R value is also called the correlation. If you look up here at the top, it says, what does the correlation R tell us about the relationship between two quantitative variables? So now that we've gone through and we've described the strength and the direction of all of these, I want you to look at their R values. And then I want you to answer question number 1 on your page. Look at the R values, look at how we described them, and tell me what you think that correlation R is measuring. Write it down on your page first. As I drop things, let me throw $100 calculator at you.
Thank you, ma'am.
You're welcome. All right. So again, if it says what is the correlation measuring, that means the R value. What do you guys think the R value is measuring here? Yes. It tells us the strength and the direction of a linear relationship. How closely the points follow a line. Tells us about the strength and the direction of a linear relationship. So R is always going to tell us how closely those points follow a line pattern. How closely the points follow a linear pattern. So looking at this scatter plot here in number 2, would you describe this as a positive or a negative correlation? Positive. Weak, moderate, strong, or very strong? I would go with moderate. All right, so now using those other R values as a guide, I want you to come up with your best guess for what you think the R value is here. Write it down on your page. So what do we think? I heard 0.67 first. All right. The actual R value for this scatter plot is 0.551. 0.551. All right. I would like you to try the same thing now on number 3. Try the same thing on number 3. Oh, I already handed you one. My apologies. Try the same thing on number 3.
Are you dumb? You just did that, Are you
You're welcome. All right. Positive or negative? Negative. Weak, moderate, strong, or very strong? Very strong. What's our best guess for an R value here? I heard 0.98 first. That's just, I'm going with the first thing I heard. That's the first thing that I heard. The actual R value for this scatter plot is negative 0.994. Why the negative on there? Because it's going down. So negative 0.98 would be our guess. Negative 0.994 is the actual R value there. All right. Let's go ahead and flip the page over. Here are the data for one group's Barbie bungee from yesterday. Number of rubber bands from 0 to 7, and then they have the distance traveled. Should be centimeters, not inches. Those would be enormous rubber bands if she traveled 30 inches. Let's go ahead and change that. I'm irritated that that says inches. Should be centimeters. All right. They give us the R and the R squared value, but there's a homework problem where you are asked to find R. So I want to show you on the graphing calculator how we can find R. So everybody should have a graphing calculator now. All right. First thing we need to do on the graphing calculators is turn on the function that will show us R. And unless the calculator is reset, this won't have to be redone every time. But all of these calculators got reset over the summer, so we have to turn it on. So you're going to push the second button and 0. The second button is blue, and so this is going to access the catalog. It's written in blue above the 0. Do you guys see that there? All right, we need to jump to the D section, so we're going to press the X to the -1 button, and there should be a green D right there. That'll jump us into the Ds. We're going to scroll down until we see it says diagnostic on. All right, that's okay. I'll go back and do it again. So we start with the blue second button, and then you push 0. Blue second button and 0. This opens up the catalog. Do you guys see how above the 0 in blue it has the word catalog? That's what we just opened up. We're going to jump now. This is like all the different functions that the calculator can do. Some of these functions have to be turned on, and that's what we're going to do now. We're going to turn this function on. We need to get to diagnostic on, which is in the D section. You can just scroll there, but it's going to take you forever. You're going to have to go through all the A's, then all the B's, then all the C's. So we're going to jump to D by pushing the X to the -1 button. It's right above X squared. If you see, there's a green D right there. Do you see how that jumps you right into the D's? Now we're going to scroll down until we see diagnostic on. So right here where it says diagnostic on, you want the little caret, the little arrow pointing to that. You're going to hit enter. That's not enough yet. You selected it, but you didn't actually turn it on yet. You now have to hit enter again, and it should have the word done show up on the screen. Now you've turned the diagnostic on. You don't have to do that again unless the calculator gets reset. All right, so we don't have to do that each and every time. But when you're doing this on like the calculator app on your phone, you're probably gonna have to go in and turn the diagnostic on. All right? Okay, so now we're gonna go to where it says stat right here by these arrow buttons. We're gonna click on edit. If there are numbers in these columns, in these rows and columns, you're gonna go up and highlight the name of the list. So here I have it highlighted at L2. You hit clear and enter, and it wipes the whole thing out. So then I'm going to arrow over to my other list. I'm going to highlight the name of the list. I'm going to hit clear and enter, and it clears it all out. List 1, L1, we're going to put the X values from the table here. The number of rubber bands. We're going to go from 0 to what on number of rubber bands?
7.
0 to 7. So 0, enter. 1, enter. You have to hit enter after each number, or it won't put it on the table. Make sure you hit enter after the last number so that it puts it on the table.
I just press down.
You can press down, but make sure that it enters your last number. But yes, you can press down or enter. The point is you can't just enter the number and leave it at that. Yep. Okay, hit stat and enter.
Oh, thank you.
You're welcome. All right, in list 2, we're going to put the distances that the Barbie doll traveled. So that Y row. So 30, 34, 45, 46, 56, 58, 66, and 78. Oops.
Will we get multiple
78.
problems like this on one
No.
section?
No, you should not get multiple problems like this. All right. So far, so good with putting our data in? All right. We're going to hit the stat button again. So stat right here by the arrow keys. This time we're going to arrow over to where it says calc. And we want option number 8 down here. Option number 8, where it says lin reg A plus BX. Option number 8. You want the X list to be list 1. You want the Y list to be list 2. There should not be anything where it says frequency list or store reg EQ. Nothing there. We're going to go to calculate and hit enter. That's okay. Yep.
And then click on it.
So you go to stat and edit. Stat edit is where you enter your values.
Oh,
And then stat calc. And we want option 8.
I'm right here. Let's go.
Come down to calculate. Hit enter. There you go. All right. How we doing? Do you guys see this on the screen? If you do not see this on the screen, let me know so that I can help you get there. Hit enter.
Oh, okay. That's all I have to do.
Yep, that's all you have to do. Go down, use the arrow keys to go down to calculate. Oh, sorry, you need L1 in there. So second and the number 1. There, now arrow down. Go to calculate, hit enter. There we go. All right. Do you guys see the R squared and the R? R squared is right here. If we round this to 3 places, that would be 0.974. If we round R to 3 places, that would be 0.987. So far, so good? That's where they came up with these numbers up at the top of the table, R squared. If you guys need directions for how to type this into the calculator, please let me know. I'm happy to provide written directions for how to put this into the calculator. Yep, let's do that at the end. All right. We're going to talk about R squared here in just a minute. All right, so this is the data for one group's Barbie Bungee. After class, the group came back And they did the Barbie bungee again, but with 12 rubber bands. This dot right over here is representing what they did with the 12 rubber bands. This was the length, or the distance traveled. How do you think adding that point to this data would affect the R value? How do you think it would affect the R value? You don't think it would change very much? Would it change at all? It would change.
But it's still kind of linear and like positive.
It is linear and it is positive. Did it become more linear or less linear? More linear. What did we say the R value was showing us again? Correlation, the strength, how much like a line the data looks. So here's my data and like a line of best fit through my data. If I extend that out, it pretty much goes through that dot. So that strengthens my overall correlation. If it strengthens the correlation, R is going to get closer to what number? 1. R is going to get even closer to 1. It's already pretty close to 1, but R is going to get even closer to 1 because the data becomes more linear. All right. Let's look down at number 5. The group accidentally typed in 85 for 5 rubber bands instead of 58. When they measured it, it was actually 58, but when they put it into their calculator, they accidentally typed 85, resulting in this dot right here. How will that point affect the correlation? How will that point affect R? It's going to have a negative impact, so R would get closer to what? R is going to get closer to 0, yes. R is going to get closer to 0 because it makes the data less linear. Would it say what? The problem is that we can also have very strong negative correlations, like a -1. So that would get me farther away from 1, but not necessarily into the weak territory. Yes? It's weaker means it's less linear. Yes. All right, so this point up here does not follow the linear trend. Does not follow the linear trend. You okay, Solomon? Back in the previous example, that point that they added up here follows the linear trend. Follows the linear trend. All right. Let's look at interpreting R, and we're going to talk about R squared now too. Template for interpreting the correlation. If you are asked to interpret the correlation or to interpret R, the sentence frame that we're going to use for that is the linear relationship. R always tells us how close it is to a line, so we're always looking at linear relationships when we're talking about R. The linear relationship between the explanatory variable and the response variable is, and then we'll give the strength and the direction. So I want you guys to interpret the R for the Barbie data at the top of the page. What was the R value for that? 0.987. Take a moment to write down the interpretation using the sentence frame. Write down the interpretation using the sentence frame. That's okay. We're right down here. So what would this sentence sound like?
The linear relationship between the number of rubber bands and distance traveled is very strong. Positive?
Yes, I love it. That's perfect. The linear relationship between the number of rubber bands and the distance traveled is very strong and positive. That's exactly what I had written. The only other thing that I would add to something like this is to make it really clear which one is my explanatory variable and which one is my response variable. So next to number of rubber bands, I would put an X. And by distance traveled, I would put a Y. Just so I'm really, really clear about which one is the explanatory and which one is the response. But R, the correlation, is always telling us about a linear relationship here. So we're always going to start with the linear relationship between. All right, interpreting R squared. This is called the coefficient of determination. The coefficient of determination. And the way we interpret that one in context is R squared written as a percent. So R squared percent of the variation of the response variable is explained by the linear relationship with the explanatory variable. What was R squared from up at the top of the page? 0.974. I want you guys to use that sentence frame and interpret this R squared value. What would our sentence sound like? What's it going to start with?
7.4% of the variation of the distance traveled is explained by the linear relationship with the number of rubber bands used.
Perfect. That is 100% perfect. 97.4% of the variation in distance traveled is explained by the linear relationship with number of rubber bands. All right, so now let's talk about what that means. When you look at the table up at the top of the page, do you see how the Y values keep changing? It's saying that the way those numbers are changing, 97.4% of the way those numbers are changing is directly because of how many rubber bands were used. So using that, I would be able to make pretty accurate predictions for more rubber bands. Although we were getting bounce towards the end, right? That's why it's not 100% of the variation. We had some bounce in the Barbies. If you think about your job, if you've ever had a job, 100% of the variation in your paycheck is because of the linear relationship with the hours that you worked. So all of the change in your paycheck is because of the hours that you worked. Here we had some bounce in the rubber bands, so not all of the differences in the Y's are because of the rubber band, but most of it is. Does that make sense?
Yeah.
All right.
With
Can I what? Leave it up a little longer? Yes. You're welcome. All right. Flipping it over to the next page. Learning topics. We had 3 learning targets for today. Correlation, which is R. The correlation is R. Tells us the direction, positive or negative. The form, when we're talking about R, is always linear. And the strength will be a number in between positive 1 and negative 1. If it's negative 1, that is a perfect negative correlation. If it's closer to positive 1, then that's a perfect positive correlation. If it's close to 0, that's where we get weak. The closer you get to 0, the weaker the correlation becomes. And we say the linear relationship between X and Y is, and then we tell our strength and our direction. Learning target number 2, the coefficient of determination, or R squared. This tells me the percent of the variation in Y is explained because of the linear relationship that it has with X. And then our last learning target, which we're going to touch on just very briefly, correlation does not equal causation. Just because 2 things happen together a lot does not necessarily mean that one is causing the other. If I'm in the habit of anytime it's overcast in the morning, grabbing my umbrella before I walk out the door, and it happens to rain most of the time that happens, that doesn't mean that me bringing my umbrella is causing it to rain. All right, let's look at the check your understanding now. Tyler Vegan, this is true, by the way. Tyler Vegan wrote a book called Spurious Correlations, in which he investigates relationships between quantitative variables. One example in the book is the strong correlation between the number of letters in the winning word of the National Spelling Bee and the number of people who died by venomous spider bites in a given year. Here are the data for an 11-year span. Letters in the winning word, and in that same year, the deaths by venomous spider bites. I want you guys to do part A, the correlation R between the numbers of letters in the winning word of the National Spelling Bee and the number of deaths by venomous spider bites is 0.806. I want you to interpret that value. Interpret that value.
I had a dream.
Process correlation is not equal causation.
Do you have a question? What's your question?
And the R says that it's really strong.
You're going to say the linear relationship between the X variable, which you're going to name, you're going to write it out, and the Y variable, you're going to write that out in context, is, and you're going to use the R value to determine your strength and your direction. So that actually is a fairly strong correlation. If I were to draw in a line, they're not perfectly in a line, but they're pretty close. There's certainly a lot more than like the clouds that we were seeing on that first page. Oh, yes. Yep, there's still a correlation here, even though it's a ridiculous correlation. Yes, yes. All right, what would this sentence look like? How's it going to start?
The linear relationship between letters and winning word of National Spelling Bee and deaths by venomous spider bites is moderate and positive. Is it moderate?
I would call it a strong relationship.
Okay, so
I would call it fairly strong. So with an R value of 0.806.
even when the graph looks like that, that's still
Mhm.
very strong.
That is still considered, I would say fairly strong. I wouldn't necessarily say very strong, but I would say that that is fairly strong. So here's the thing. When I look at the data and I draw in a line of best fit, those dots do hug fairly close to that line. The dots are fairly close to the line. It's not like those clouds on the front page, those first 6 graphs that we were looking at, where they had a much more cloud-like appearance to them. I think if you were to zoom out on this, it would appear stronger. I think we're zoomed in so close on this graph that that's why it has maybe less of a strong appearance than the R value is indicating.
Like if the data was R5s, they would be a lot closer.
Yes, yes. The only other thing that I would add to this is I would say X is my number of letters and deaths by spider bites is my Y. That's the only other thing that I would add to this. Number 2 says to calculate and interpret the coefficient of determination, R squared. They didn't tell us R squared. How are we going to find it? It says to calculate it. Square R. Take 0.806 and square it on your calculator. What do you get when you do that? 0.649636, so about 0.65. I want you to use the sentence frame up at the top of the page to interpret R squared.
Like 64.9.
I'd be fine with 64.9 or 65 because we're going to soften it up. We're going to say about anyway.
I should say about.
I would still say about, yes, because that R value already had to be rounded. So when we take that number and we square it, we're going to introduce some more error into it.
You're literally a child.
I try my best, bro.
You're only a kid for so long.
When do you turn 18?
What would this sentence be? In Y. So what is our Y?
In the death by venomous spider bites is explained by the linear relationship with the number of letters.
Yes. Yes. About 65% of the variation in deaths by spider bites can be explained by the linear relationship with number of letters in the winning word. Which is to say that if I know how many letters there are in the winning word, I could make a reasonable prediction about the number of people that died by venomous spider bites.
No, you can't because that is stupid.
Actually, no, you can. 65% of the variation. You could, the point is, even though this correlation is ridiculous, it can still be used to make reasonably accurate predictions. Even though the correlation makes no sense, it does have a relationship, and you could still use it for the purpose of predicting. Sometimes there's some relationships that seem ridiculous, and we find out later that there's something going on in the background that explains why they have this relationship. Sometimes it's just ridiculous.
Yeah, sometimes it's just stupid.
Yes.
I agree, bro.
But you can make a more accurate prediction with this information than without it. But that leads us to our last question now. There's a strong correlation between these two variables. Does that mean that the longer winning words in the National Spelling Bee caused an increase in the number of deaths by venomous spider bites for that year? No. There's correlation but not causation. Absolutely correct. A strong correlation between two variables does not mean that one caused the other one. A strong correlation between two variables just means that these two things go together a lot. But it does not mean that one caused the other.
Now, if you somehow end up with a correlation of exactly 1,
It still does not show causation, because there could be something that is causing both of these things that you see the correlation with. There could be some third reason that is the cause for both of them. Did you have a question? That's a good question. What thoughts do we have about that? How would you show causation? Do more tests. Specifically, what kind of test could do this? An experiment. An experiment is how you show cause.
So in this case, we would never have a situation where.
If all we have is a correlation, all we have is a scatter plot, we have data for X and we have data for Y, all we could say is that these two things have a close relationship or they have a weak relationship or a moderate relationship. Knowing one would help me make better predictions about the other, but I don't necessarily know that one is causing the other one. All right. Those of you that were struggling to follow along with the graphing calculator directions, I don't have enough time to write down all the directions on the board right now. However, I do want to remind you, I take a video of class each and every day, and it shows the screen at the same time. So you can watch the video for how to turn on the R and R squared, and how to enter the data into the calculators. Please put the graphing calculators back in the suitcase before the end of class.